All right, welcome to LTHS Physics C, and this is going to be a work energy example with conservation of mechanical energy. And this is going to be a long one, so it's going to take a lot of work to get this one done, so I hope you got a lot of energy. Buckle up, here we go. So, what we're going to have is we're going to have a block on a ramp pushed up the ramp by a spring, and we're going to ask some questions about the motion of the block, okay? And the block could be something about akin to your book bag. So here's our ramp, and I'm going to draw this pretty big, all right? The ramp's at an angle theta to the horizontal. The spring is attached to something solid there, as a pin or something like that. Here's our spring, okay? And you have compressed the spring. You pressed it down, okay, and we'll call that X naught for now. And that's how far you've compressed the spring. We're going to throw numbers at this in a little bit. And then you put your book bag up against that spring. It's got a mass M, okay? Some other things you need to know. Of course, there's friction. So there is a mu sub k. We're going to be sliding along, so we're going to have sliding friction. So let me throw the numbers at you. Here are the givens, okay? Let's see, X naught is 10 centimeters, okay? The spring constant is 2 kilonewtons per meter. Okay, we use kilonewtons per meter because we're cool. The coefficient of sliding friction is 0.3. The angle with the incline, we'll go ahead and use our 30 degrees, okay? And the mass of your book bag is about 5 kilograms. Now that'd be a pretty light load for most of you, but hey, we'll go with it. So here's what we're going to find, okay? I'm going to write the first one down, and then the other ones I'll tell you later because it's going to take another board. The first thing I want to know is where and when is the velocity of that backpack a maximum. So what I want to know is what is X and what is V max, okay, when that happens. Now, a lot of people, a common misconception would be to say, the backpack reaches a max velocity at the end of the spring. Well, actually at that point it's already slowing down. There's a point somewhere here where the spring is pushing on it, and it's reached its max velocity and actually begins slowing down. Now, something to note, where this happens, the X value we're trying to find is what's the new final compression of the spring when the backpack has reached its max velocity. That X is measured from here. That's 0. This is the spring compression. So we're trying to find from here how far is the spring still compressed. When do we reach max velocity? What do we know at max velocity? Well, if you're at a maximum velocity, you're done accelerating. Your acceleration is 0. You're done speeding up. If your acceleration is 0, then what else do we know is 0? Your net force, okay? So we need to draw an FBD, and we need to set our forces equal to 0 and figure out what that value of X is. So I'll do that right here, and I'm going to go ahead and go right to component form for the FBD. So here's our backpack. We know we have the two components of gravity acting on it. That is mg sine of theta and mg cosine of theta. We know we have the spring pushing on it, otherwise it wouldn't go up. So that is force of the spring, the magnitude of which is kx. And that's pushing the backpack up, so I've got the direction written right. We also have a normal force, which in this problem is going to equal mg cosine theta because there's no other forces perpendicular to the incline, and the backpack ain't accelerating perpendicular to the incline. Finally, we've got friction. So we got the force of friction, okay? All right, so when is the acceleration going to be done? Well, when this force equals these two forces. So I'm going to set this equal to these two. That means my net force is 0, which means my acceleration is 0, which means I've reached my max velocity. So I'll do that up here. We know that the spring force has to equal the force of friction plus mg sine of theta. For formulas, we've got Kx. Force of friction is mu sub k times the normal force, so it's mu Fn. And in this problem, we recognize that Fn is equal to mg cosine theta. And that plus mg sine theta has to equal Kx. So I'm going to do a little math here first. So x is going to equal this plus this over k. I can factor out the mg. So you got mg times mu sub k cosine theta plus sine theta all over k. So that if they asked you for an expression for the x when our backpack has reached the max velocity, in terms of the givens and with variable form, that's it. Now we're going to get a number out of this. So we sub in all our numbers. M is 5. G is 9.8. So that's all 49. Mu sub k is 0.3. Cosine of 30 plus sine of 30 all over k. Now it's 2 kilonewtons per meter, which is 2,000 newtons per meter, and you get x max. And that's where the backpack reaches max velocity from here down. And if you do the math and you can verify this, you get 0.0186. 0.0186 meters, or 1.86 centimeters. So it was compressed 10 centimeters. We're just a little over 2 now. So we've gone over 80% of the distance that the meter was with the spring was compressed, but it's not fully uncompressed yet. So that's where the max velocity occurs. Now, what is that max velocity? Well, that's a whole other ball of wax. So what you're going to do is you're going to use, well, one way to do it is to use conservation of energy. This is probably the easiest way to do it. Our 2 points, when you use conservation of energy, you need 2 places to compare. So this is our point A. Where the backpack has reached max velocity, which is about here, that is going to be B. Okay? And we're looking for the velocity at point B. So at point A, I'll write the equation out first, the general equation. So we've got some potential energy at A. Maybe there's some kinetic energy at A. Maybe there's not some non-conservative forces acting on the backpack. And then at point B, there might be some potential energy, and there might be some kinetic energy. Okay. Well, there is one term out of these 5 that is 0. At point A, the backpack ain't moving. That's 0. Okay. Everything else, there's at least one part of each term. Potential energy at A. Well, we've got 2 forms of potential energy happening here. The spring, if it's compressed at all, it's got some potential energy. And we've got changes in height. So you got to measure gravitational potential energy. For gravitational potential energy, I'm going to call point A 0 and just measure everything from point A. Now, for the spring, you don't have a choice. For the spring, this is 0 when it's uncompressed, so you have to work with that. So gravitational potential energy and spring potential energy have different 0 places, okay, at least in my drawing. I could have made this point 0 for gravitational and then measured from there, but I'm not going to do that. So at point A, we do have, the spring is compressed, so we've got U elastic at A, but there's no height there, so there's no gravitational potential energy. The work done that's non-conservative, well, you have the spring and you have gravity. Those are both conservative forces. Those are both going in our potential energy terms. The one non-conservative force that's acting, well, there's 2 non-conservative forces acting. There's the normal force and there's friction. The normal force, however, doesn't do any work because that force is perpendicular to the motion. So normal force I can ignore as far as work. Friction, on the other hand, is doing work, and it's doing negative work. As the backpack moves up the incline, friction points down the incline, so that's negative work. So I'm going to put a plus the work done by the force of friction, but that value is going to be a negative value when I plug it in. that equals the potential energy at point B. Well, at point B, you got a couple things going on. The spring is still compressed a little bit, so you've got some elastic potential energy, but you've also got some height. So now you've got a gravitational potential energy. I'll put UG at point B. And of course, the backpack is moving. I'm trying to find the max velocity, so we got kinetic energy at B. Okay, so now, once you've got that figured out, now it's just being very, very careful with details. And this is where you're most likely to get stuck on something, is writing in the details. So elastic potential energy, that's 1/2 K x naught squared. Okay, that one's pretty easy. Work done by friction, I'll put minus the force of friction times what distance? Well, it's not x naught, because the backpack doesn't go 10 centimeters. It's not x final, because the backpack doesn't go 1.86 centimeters. It's the change in those two. It's the difference between 10 and 1.86 centimeters. So it's x minus x naught. Now, when you do that, you just want the magnitude of that. You don't care if one's bigger than the other. You just say, how far did it go? In other words, what distance did the backpack slide? This equals elastic potential energy at point B. That's 1/2 K. Well, that is x final squared, which is our x final that we found here, our 0.0186 meters. Okay. Plus gravitational potential energy. Well, that's mgh. What's h? All right, well, the hypotenuse that the back traveled was delta x, or x minus x naught. The height would be that hypotenuse sine of your angle. So that height, and again, this is where the details get crazy here. You've got your x minus x naught sine of the angle. That is your height that the backpack went up. And then you've got the kinetic energy of the backpack, which is 1/2 mv. I'll put Vm squared, because that's our Vmax squared. Okay. So now it's just a matter of plugging all the numbers in very carefully and getting your Vmax. So I took the liberty of doing a little bit for us. So I'm going to show the numbers first. We got 1/2 times 2,000 times x naught, which is 0.1 meters squared. Okay, that all ends up being 10, all right, minus the force of friction, okay? Well, force of friction, I can't put a number in there. Yeah, I gotta put the expression. It's mu sub k times Fn, which is mg cosine of theta, times x minus x naught, okay, equals, and then the right side is all set up, okay? Next line down, we'll throw our numbers in. So we've got 1/2 times 2,000 times 0.1 squared minus 0.3 times the mass, which is 5 times 9.8 cosine of 30. X minus x naught, it was 10 centimeters, and now it's, or 0.1 meters, now it's 0.0186. So I'll write it out that way. It's 0.10 minus 0.0186. That's our delta x. And again, you want a positive magnitude there, so I'm putting that one first. So that's this expression here, equals 1/2, k is 2,000, x final, which we got up there, was 0.0186. That's where the backpack reaches its max velocity. Make sure you square that. Plus 1/2 the mass of the backpack, V max squared. The only number we don't know in that whole entire mess is Vmax, okay? So I would recommend you try plugging these numbers in and make sure you can get the right answer. But the answer I got, and hopefully you match it, is 1.63 meters per second. Which, by the way, isn't all that exciting. It's only about 4 miles an hour. So, yeah, a lot of whoop to do about going 4 miles an hour, but hey, there you go. So that's the first half of this problem, or a little more than half of it. So what have we found so far? We found where the backpack achieves its max velocity, and then we use conservation of energy going from one point to another. And remember, when we do this, That's one point. That's the other. And the work non-conservative is what happens in between, okay, as the backpack slid from one point to another. We were very careful with details. This is where people often have a hard time with these kind of problems, is being very careful with what details. There's like 3 distance values. There's an x naught, there's an x final, okay, here, okay, and there's also the delta x at the backpack travel, and you had to use all 3 in this problem. Now the last part of the problem is how high up does the backpack go from the initial position till it stops. So it's going to release from the spring, it's going to slide a little bit, and then it's going to stop. So how far does it go before it stops? So I'm going to go ahead and I'll use this board. And I will start that part of the problem here. So how far up does the backpack go? And we'll call that D stop. From its initial position, which means right here, from point A. So basically, it's going to go to some other point, somewhere up here. I'll call that point C, and it's going to stop, okay? So in this part of the problem, you've got 2 choices. You're going to use conservation of energy, and you're going to go from A to C or B to C. Both will work just fine. If you find B to C and you get that distance, then you got to add on this distance, which we know. However, in my opinion, it's easier to go from A to C because I've already gone from A to B, so I know everything about point A already. So I'm going to go from A to C, okay? And I'm going to use conservation of energy. So I've got K naught plus U naught plus work non-conservative equals K final plus U final, okay? Now the cool part here is if you do A to C, you got a couple zeros. The backpack starts from rest, and when the backpack gets all done sliding, it's at rest again. So both kinetic energies are gone, okay? U final, we're going to measure our height from point A again. So our U naught is just spring potential energy, so U elastic at point A, just like before. Like before, the only non-conservative force that's doing work is friction, so it's minus force of friction times D stop this time, so it's not X or anything, it's D stop. I don't know how far that is from A to C. This equals U final. Well, what kind of potential energy does the book bag end up with? Gravitational. So that's mgh, that's U final. This is 1/2 K x naught squared minus friction, which is mu mg cosine theta, so that's mu times F normal times D. We're trying to find D, that's our unknown, and that equals mg. What about H? Well, if this is D, we need H, which is simply the opposite leg in that right triangle. So H is just D sine theta. Again, details, right? Now, we got D in 2 places in our equation here, so you got to be a little careful. All right, so I'll plug some numbers in here. We've got, let's see. I'll do this right here. So I got 1/2 times 2 grand times 0.1 squared minus mu, which was 0.3, m, which is 5, g is 9.8, cosine of 30 times d equals m, which is 5, g is 9.8, sine of 30, which is 1/2, times d. So we got d in 2 places. I got to do a little algebra here. I ended up getting 10 for that. For all this, I got 12.73 d equals, and here I got 24.5 d. And I end up with, if I do this, you get 10 equals 37.23 d, and d ends up being 0.269 meters, or 26.9 centimeters, okay? And that is, since we measured from A, that is exactly how far the backpack slides total in its motion. So about 16.9 centimeters from the end of the spring, 26.9 centimeters total. So that's a fairly long example involving conservation of energy and finding different things about the motion of an object using conservation of energy. So thank you very much.